Welcome back. Next up is Roman from Nagra. He's going to tell you all about how to secure your IoT devices. Enjoy his talk.
Hello, my name is Roman Korkikian. I'm hardware security expert at Korkikian. Today I'm going to briefly demonstrate you Sidechannel and fault attacks and how they can be applied on an end device. I would like to highlight that the discussed attacks they can be applied on any semiconductor device, not only on the LoRa end device. Any smart card, set-top box, system on chip are potentially vulnerable to sidechannel and fault attacks. LoRa does speak about physical security and about sidechannel and fault attacks. At least I found one mentioning that secure key storage, provisioning and usage shall be performed by secure elements or by hardware security modules. And those two are usually well protected against sidechannel and faults. I work for Korkikian IoT. Korkikian Group, it's a big company and it has four main business directions. So the first one it's Korkikian IoT, where I belong to. The second one, Nagra Korkikian. It's the number one in the world regarding content management solutions for operators, for digital TV operators. There is a fast-growing branch called Korkikian Security, so all the questions about security can also be related to this branch. And there is also public access solutions called ski data. Everything related to physical access to parking or ski resorts is presented in this direction. So when we do speak about sidechannel and fault attacks, we need to think about an end device, about a physical device. For the demonstration, I selected a general purpose microcontroller from Espressif. It's ESP32. And on the PCB, there is a LoRa modem. And LoRa modem is used uniquely to access LoRa network. So it's a physical link, let's say. All the key storage, provisioning, and handling is done by ESP32. So once again, the discussed attacks are against the ESP32 itself. How to extract the information from the microcontroller. Whenever I explain fault attacks, I usually try to explain by this analogy. Imagine yourself driving from country A to your hometown. You are using a GPS navigator, so you, let's say, performing some algorithm or some calculations. You go from point A to point B by using navigator. And right now you're at the moment when you need to take a critical turn. If you take a wrong turn, you need to go other 40 kilometers. So you are concentrated, you're on the road, and at this particular moment, someone calls you by phone, or someone in the car asks you a question, and you lose the concentration and you make a wrong turn. So in fact, this situation can be considered as a fault attack. A fault injection is when someone is calling you or when someone perturbs your concentration. And the fault effect is the wrongly selected path. So you see fault injection and the end result that the computations are wrong. The same situation can be applied against semiconductor devices. A semiconductor device, any device which you connect to the network or use on daily basis, is based on semiconductor, logically. It requires certain physical conditions to be in normal range. For example, power supply to the device shall be constant and shall not be, let's say, smaller than 1.2 volts, let's say. Also, temperature, environmental temperature, shall be in certain range. In addition to that, you would love to avoid laser or any kind of X-rays around your device because it might affect the computations inside. Imagine that for a very short amount of time, your normal conditions are no longer normal and they they go out of normal range. For example, that the power supply is dropped to zero for tenths of nanoseconds. In this case, the device is not freezed, or it's not muted, or it does not reset, but it might lead to the situation that the power drop causes wrong computation, or instruction skipping, or data modification. I will demonstrate you this specific situation by the following demo. So I selected ESP32 and I have implemented a tiny function that performs only one single loop of 5,000 iterations. Before the loop starts, I raise up a trigger, so it's a GPIO signal, and you see the rising edge on the graph below, indicating the beginning of the loop. And then during the loop, I will inject a fault. Basically, I will drop a power from normal to zero, and this fault will last for, let's say, several nanoseconds, several hundreds of nanoseconds. And then I will observe the results in the console. So in the console on the top left window, you will see only the wrong results. The bottom window, it's a snapshot from the oscilloscope. So the blue graph, it's a power supply which is given to the device. This drop, it's my fault injection, so it's intentional fault injection. The red signal is the GPIO signal. Usually it's indicating the beginning and as the end of the loop operation. So we see that the glitch is injected just after the loop has started. And if we, this is a video, if we will see the video, if we look at the video, we will notice that the chip, whenever the fault is injected, the chip returns wrong result. For example, instead of returning 5,000 zero, it returns 20, another number, 23. And if we continue the video, it will inject, you will see some other faults, 24, 27, etc. So why these numbers are changing? First of all, when the glitch is injected, it exits the loop prematurely, so your counter is not incremented to 5,000, but it remains at certain value, for example 31, 30. And second very good indication that with a bigger delay, so when the glitch is injected further in the processing of the loop, you will see the different iteration number. So you will see that your iterator is increasing. So this particular fault that I demonstrated right now, it's a power drop in the power supply of the CPU, and this fault leads to the premature loop exit. Basically, you can consider this fault as an instruction skipping. So by injecting a tiny power drop, you can skip a certain operation inside the microcontroller. And this fault is very powerful. So by skipping an operation, you can achieve many different effects. You can skip security check, you can skip signature check, for example, or you can skip an instruction which will prevent you from reading certain memory access, for example, OTP zone. And there are some other effects that can be devastating for device security. And in fact, instruction skipping was successfully used on ESP32. There is publicly available information, let's say there is a blog post, which explains how an attacker can read a secret IS key, which is stored in the OTP memory. Usually in normal conditions, this key cannot be accessed by an attacker. But when he injects a fault which skips one specific operation at one specific moment, an attacker will get access to the key, and by getting access to the key, he can decrypt the entire firmware. an attacker can extract cryptographic keys by fault injection. So if an attacker injects fault during cryptographic computation, he can compare correct and wrong results, and by mathematical functions, he can extract the secret key, which is used in these computations. To demonstrate you this attack, I have implemented IS-128 as a software white box implementation in ESP32. Usually to extract cryptographic keys you need quite many faults, but for IS-128 you only need 8 correctly placed faults in the computation in order to get full key. So in this case, you see that the beginning of IS is illustrated by the rising edge of the trigger, and the end of IS is illustrated by the falling edge of the trigger. My fault is injected in the latest IS rounds, and sometimes some faults lead to the full ciphertext modification. So by comparing wrong and correct ciphertext, I see that all bytes of the wrong ciphertext are modified. And sometimes the fault is successfully injected, and what we see, I call the diagonal. So by comparing correct and faulty ciphertexts, and if we put the ciphertext in the proper order, we will see a diagonal. And this specific fault is an extremely nice indication that our error is injected in the latest IS rounds. And with this kind of faults, with the diagonal faults, we need only 8 of them in order to get the correct IS key. So by looking at this video, we already have observed 2, and we only need 6 remained. Well, I need to say that fault attacks are quite probabilistic. You don't observe the same fault all the time, so they can be different. In our specific situation, we have observed entire ciphertext modification, diagonal modification. Sometimes it's also a reset, so our system goes into a reset mode, and sometimes it can be exception. For example, this one, it's illegal instruction, meaning that our glitch caused an instruction modification, and this instruction could not be processed by CPU. And in this case, CPU raises up an exception. There is a second powerful class of physical attacks called sidechannel attacks. To explain these attacks, usually I give example of a brain-computer interface. Whenever we think or whenever we compute by our brain consumes calories, first of all, and secondly, it emits certain electromagnetic waves. Those electromagnetic waves can be measured and transformed into commands for a computer. So, meaning that our thinking and our computation can be transformed, or they can leak certain information about what we think of. The similar situation can be applied on the device. When device computes, it loses power, it consumes power, and also it transforms power into the photonic emission and electromagnetic emission. By measuring those signals, an attacker can understand what device is doing and which data it processes. For example, I have implemented a RSA algorithm on ESP32, and I have measured only one power trace, so power consumption of the device during RSA computation. Whenever our RSA computation is performed, there is a square multiplication algorithm, and this algorithm has a loop. One iteration of the loop may or may not include if condition depending on the key value or on the key bit. So whenever we see short patterns in our power consumption, we can understand that our if condition was not performed. But if we see that the pattern is big, it means that if condition was actually computed, was performed. So by looking at one power trace, an attacker can understand which bits are 1 or 0. And these bits, they belong to the real secret key. So this is the power of sidechannel attacks. However, sidechannel attacks they can be easy if the algorithm is implemented wrongly, let's say. So RSA algorithm can be implemented securely against sidechannel attacks. But some algorithms, it's a bit more difficult to implement more secure. Usually people think that by implementing IS or RSA as a hardware IP, this will prevent from side-channel fault attacks, and this is not true. For example, on ESP32, IS is implemented in hardware. So this is a one power trace of IS computation, and in fact it's very difficult to understand where IS algorithm is here. So we see just some power consumption, and that's all. But side-channel attacks, it's a statistical tool. So by collecting many traces, in our case there are 1 million traces we are used, we can understand where the algorithm is performed and which key actually is used. So this attack involves statistic, like person-person correlation or mutual information statistics. An attacker can create a power consumption model and compare this power consumption model with a real consumption. And the power consumption model will match only for the correct key byte. So we will search IS key byte by byte. And these statistics, for example, here you see person correlation coefficient for the trace, for let's say this particular trace, for part of this trace, will give us, let's say, flat value, let's say similar value for wrong keys, but one specific key byte will pop up because the power model for this byte corresponds well with the real power consumption, and our statistics show this. Side-channel attacks are a bit more difficult to understand than fault attacks, but believe me, they are very powerful and they can be applied on various cryptographic algorithms. Clearly, you cannot skip instructions, or you cannot get access to the zones where which are protected, but you can understand which data is processed by CPU or by cryptographic routine. To conclude my demonstration, I would like to say that side-channel and fault attacks can be used to extract data from a semiconductor device. Fault attacks, in addition, can skip instruction or modify data in order to give you access to certain IPs or to certain memory blocks which are not supposed to be given. Those attacks are super well studied on IS-128. There are many papers and publications explaining attacks on IS-128. Clearly, there are mitigations against these attacks. So if you use secure elements or hardware security models, they are protected against side-channel faults by, let's say, design or architecture. However, if someone discovers a fault injection attack on a device, then it's very difficult to prevent this attack from being used, meaning that you cannot update the hardware clearly, which is in the field, which is on the market. You can only introduce some modifications in the newer versions. And fault protection or side-channel protection by software, it's not as efficient as a hardware modifications. So if you want really to test your device or to understand the level of security of your device, you really need to go to a security lab and perform real evaluation. Thank you for your attention.